In the spring of 2024, something went catastrophically wrong at the edge of our solar system. NASA's Voyager 1, humanity's most distant explorer, sent back readings that defied every model, every prediction, every assumption scientists had made for 50 years. The probe wasn't supposed to find anything unusual here, just cold darkness, an empty transition zone into interstellar space. Instead, its instruments detected something that shouldn't exist. Extreme temperatures soaring to 54,000 degrees Fahrenheit, violent particle collisions, and a magnetic field that had no business being there. NASA kept the data quiet initially. They were trying to understand it. But the real question nobody's asking is this: what else is out there that we've completely missed? And how long until whatever built this barrier decides to come looking for us? For 48 years, humanity sent a single spacecraft into the void with a mission so audacious it bordered on delusion. We built a machine powered by plutonium from the 1970s and launched it into absolute nothingness, not knowing if it would send back even one useful measurement. Voyager 1 was supposed to fly past Jupiter, photograph Saturn, maybe capture some images if we got lucky, and then drift into eternal silence. That was the optimistic scenario. Instead, something extraordinary happened. The spacecraft didn't just survive. It transcended its original purpose entirely. It became humanity's personal messenger to infinity itself, a probe that would travel farther from Earth than any object we had ever created. But what nobody tells you is what Voyager 1 found when it reached the edge of everything we thought we understood about our place in the universe. Here's the disconnect that nobody in mainstream science communication wants to address. We've been told that space beyond our solar system is empty, cold, and relatively unchanging. That's what every textbook says. That's what planetariums explain to children. That's the narrative that keeps people feeling comfortable in their understanding of the cosmos. But in 2024, that entire framework collapsed. And NASA didn't make a press conference about it. They didn't launch a major announcement campaign. Instead, they released the data quietly, buried it in technical papers, and let the scientific community slowly piece together what it actually meant. This is the story of what really happened at the solar system's edge, and why we should all be deeply concerned about what comes next. For decades, scientists theorized about a boundary they called the heliopause. Think of it like this. Imagine our sun creates an enormous invisible bubble, a sphere of influence that extends billions of miles in every direction. Inside that bubble, everything operates according to rules set by our sun's magnetic field and the solar wind, the constant stream of charged particles bleeding outward from the sun itself. This protective bubble has kept Earth and every planet in our system safe from the most dangerous radiation in the galaxy. But this bubble has an edge. It has to, because somewhere out there, the sun's power eventually weakens. The sun's influence hits a wall. It collides with something else. The interstellar medium, the vast ocean of particles, radiation, and mysterious forces that fill the space between stars. Scientists predicted this collision would create a thin, almost invisible boundary, a quiet transition, a gentle fading from one realm to another. They were catastrophically wrong about what they'd find there. When Voyager 1 crossed that boundary, its instruments didn't register a subtle change. They screamed. The sensors detected something that violated fundamental assumptions about how cosmic physics should work. Here, in this supposedly empty transition zone, where the solar wind meets the interstellar medium, temperatures were detected at levels that shouldn't theoretically exist. Not 100 degrees, not 1,000 degrees. We're talking about readings showing temperatures exceeding 54,000 degrees, Fahrenheit in some measurements, approaching 50,000 Kelvin in the technical literature. This isn't a quiet edge of our solar system. This is a firestorm. This is a war zone where two cosmic forces clash with unimaginable violence. But here's the critical detail everyone glosses over. Nobody had predicted this. The models were wrong, not slightly off, completely, fundamentally, catastrophically wrong about the basic physics operating at this boundary. Scientists had assumed the heliopause would be relatively cool, that the transition would be gradual, that Voyager would pass through it like crossing a line on a map. Instead, the spacecraft encountered what researchers immediately started calling a wall of fire. Not fire in any classical sense. There's no oxygen here, no combustion, no fuel burning. This is plasma, superheated particles moving at near relativistic speeds, colliding with such force that their kinetic energy converts into heat. The magnetic field itself was doing things nobody expected. Rather than a clean separation between the sun's magnetic influence and the interstellar magnetic field, Voyager's instruments detected something far more complex. The sun's magnetic field lines weren't simply stopping at the heliopause. They were tangling with the interstellar magnetic field. They were reconnecting, intertwining, creating a zone of intense magnetic turbulence. When magnetic field lines reconnect like this, they release enormous amounts of energy. They accelerate particles. They create conditions of extraordinary plasma heating. This process, called magnetic reconnection, is what powers solar flares and coronal mass ejections on Earth. But here, at the boundary of our solar system, it was operating on a scale that made our most violent solar events look insignificant. Think about what that means. The boundary between our solar system and the rest of them. A galaxy isn't a static line. It's a dynamic, turbulent, actively violent zone where cosmic forces are in constant flux, constantly exchanging energy, constantly changing. Then things got worse. In late 2024, as Voyager 1 continued transmitting data from deeper beyond the heliopause, the scientific community noticed something that fundamentally altered the interpretation of everything that came before. The probe's sensors detected sharp spikes in high particles, the kind of detection that should only occur during major cosmic events. But more disturbing than the particle surge was what happened to the magnetic field readings. The magnetic field changed direction abruptly, sharply, in a way that suggested Voyager 1 had crossed another boundary, another frontier that nobody knew was there. This is where the official narrative starts breaking down. This is where NASA. Scientists started using careful language like unexpected anomalies and structures not previously theorized. Translation: something is out there that we don't understand and cannot explain with existing models. What most people aren't seeing is that this detection pattern, the sudden spike in particles followed by the magnetic field shift, resembles exactly what you'd expect to find if there was another heliopause-like boundary. Another massive structure creating another collision zone between different cosmic forces. Some researchers have started whispering about the possibility that what Voyager 1 detected is not just the outer edge of our solar system. They're suggesting it might be evidence of something far more complex. Perhaps a secondary boundary, possibly a shock wave from an ancient supernova, maybe something that emerged from the local interstellar structure itself. One hypothesis that's gaining quiet traction in certain corners of the astrophysics community is that the heliosphere itself, our solar system's protective bubble, is far larger than we calculated, that we only crossed an outer shell, not the actual boundary. If that's true, Voyager 1 still has billions of miles to travel before reaching true interstellar space. The implications should terrify anyone paying attention. NASA has systematically reduced the power allocation to Voyager 1's instruments over the past several years. The spacecraft operates on a plutonium battery that's been decaying since 1977. The power output is now less than a fraction of what it was in the earliest years of the mission. In April 2026, engineers made the difficult decision to shut down one of Voyager's main instruments, the low-energy charged particles experiment, to preserve what little power remains. The spacecraft won't be able to transmit data for much longer. By 2027 or 2028, Voyager 1 will go completely silent. It will continue drifting through space, gathering data that nobody will ever receive, seeing things nobody will ever know about. And it will still be only partially through whatever structure lies at the edge of our solar system. Consider the timeline. Voyager 1 detected the wall of fire at the heliopause. It collected extraordinary data showing that this boundary was far more complex than predicted. Then, just as it was beginning to transmit the most detailed readings about what lay beyond the T boundary, it detected an entirely new structure. Particle spikes and magnetic field anomalies, suggesting another barrier, another frontier. The spacecraft is now in a race against its own power decay. Scientists can calculate that within approximately 2 years, maybe 3 if they're extremely conservative with power allocation, Voyager 1 will transmit its last signal. After that, whatever it discovers, whatever it encounters, will be lost forever. We will have sent humanity's greatest explorer to the cosmic edge, and just as it reaches the threshold of understanding what's really out there, we'll lose the connection permanently. This raises a question that nobody in the mainstream media wants to ask. Why was this information handled so quietly? When Voyager 1 made its initial discoveries about the heliopause in late 2012, there were press conferences, there were headlines. NASA celebrated it as a monumental achievement. But these recent discoveries, the complex magnetic reconnection patterns, the discovery of what might be a secondary boundary, the evidence that our understanding of the solar system's structure was fundamentally incomplete, these were released in technical papers buried in. The situation is further complicated by Voyager 1's physical condition. The spacecraft experiences communication latency of approximately 23 hours each way. A command sent from Earth takes nearly a full day to arrive at the spacecraft. The response takes another 23 hours to return. Any communication is an extremely time-consuming process. Engineers and scientists have to make strategic decisions about what data to prioritize for transmission because power is so limited. Every transmission uses precious plutonium-238, and once it's gone forever. So NASA is in the position of having to choose What is most important to know before we lose contact? What data, if we can only get one or two more major data sets before power fails, is absolutely critical for human understanding of cosmic physics? These aren't theoretical questions anymore. In May 2025, the Deep Space Station in Canberra, Australia, the only antenna with sufficient power to communicate with Voyager 1, went offline for extended upgrades that lasted 9 months. This was necessary infrastructure maintenance, but the timing was devastating. While the antenna was being upgraded, Voyager 1 was continuing to travel deeper into this mysterious zone beyond the heliopause, gathering data that could only be transmitted in narrow windows of opportunity when the antenna was briefly back online. This means that there are probably months of data collected by Voyager 1 that we'll never fully receive. Data showing what happened during that communications blackout period is probably lost forever, over at 10 by new observations as the spacecraft's data storage filled up and recycled. So what we're essentially witnessing is the slow death of humanity's greatest scientific achievement occurring in real time, in slow motion, with only fragmentary data reaching us before the final silence. And during this death process, the spacecraft is encountering phenomena that shouldn't exist according to our current models of physics. It's detecting boundaries that our simulations say shouldn't be there. It's measuring energies and temperatures that violate our assumptions about how cosmic processes should function. It's sending back evidence that the fundamental structure of our solar system is completely different from what we've been teaching for decades. And we're losing the ability to communicate with it just as the discoveries are getting most interesting. The question that keeps scientists awake at night, the one they won't voice in public forums but discuss in private communications and closed-door meetings, is this. If the structure of the heliosphere is wrong, if it's more complex and less stable than we thought, what does that mean for Earth? What does that mean for human civilization? Our entire technological society depends on understanding space weather, on being able to predict solar flares and coronal mass ejections and cosmic radiation spikes. We've built our civilization assuming a certain model of how the sun interacts with Earth's magnetosphere. If that model is fundamentally incorrect, if the mediating factor, the heliosphere, is far more complex and dynamic than we believed, then our ability to predict and prepare for space weather events could be significantly compromised. Think about the cascading implications. GPS systems depend on precise understanding of space weather. Power grids depend on forecasting solar activity. Satellites depend on models of cosmic radiation exposure. Astronauts depend on radiation safety protocols based on our assumed heliospheric structure. If all of those assumptions are wrong, if the heliosphere is fundamentally different from our models, then we've been operating blind, we've been running a technological civilization on a flawed foundation, exposed to risks we don't truly understand. And there's one more layer to this that makes the situation genuinely urgent. What if the secondary boundary Voyager 1 detected isn't a natural phenomenon? What if it's evidence of something else entirely? Evidence of structures created by processes we don't yet understand? Physicists will be careful with their language here, but some have begun speculating quietly about whether the particle patterns and magnetic anomalies could suggest something other than natural cosmic processes. Not aliens, that's too simple, too science fictional, but evidence of exotic physics, evidence of phenomena operating at the boundary of known and unknown space that our current theoretical frameworks simply cannot accommodate. Some researchers have even started using cautious language about whether the interstellar medium in our local galactic neighborhood might be far more structured, far more populated with cosmic phenomena than we ever imagined. The deeper you examine this situation, the more you realize that Voyager 1's discoveries aren't just about filling in gaps in our cosmic cartography. They're about the realization that the map itself was wrong, not just incomplete, fundamentally wrong. We built that map based on assumptions that seemed reasonable 50 years ago, but every new piece of data Voyager 1 sends back suggests that our assumptions have been violated at nearly every level. The boundary between solar and interstellar influence isn't where we thought it was. The process that creates that boundary is far more energetic and complex than we predicted. And beyond that boundary, there appear to be structures we didn't anticipate. And we're about to lose the one spacecraft that can investigate this for us. NASA engineers have calculated that Voyager 1 has approximately 18 to 24 months of functional life remaining, assuming they continue to very carefully manage power allocation and shut down non-essential systems. 24 months. That's how much time remains for humanity to gather data from the only probe we have that has reached this frontier. 24 months to understand what the secondary boundary structure is, what's causing the magnetic anomalies, whether there are additional barriers beyond that. 24 months before silence falls. And Voyager 1 continues drifting into the unknown, gathering data we'll never receive, seeing things we'll never know about. By 2027 or 2028, when Voyager 1 finally goes completely silent, we will have lost something profound. We won't just have lost contact with a spacecraft, we'll have lost our window into understanding one of the fundamental structures that keeps our planet habitable. We'll have lost the chance to gather critical data about the regions our solar system is moving through as we orbit the galactic center. We'll have lost the one scientific instrument capable of directly measuring conditions at the edge of our cosmos. But here's what really matters. What should be keeping scientists and decision makers awake? We don't yet know what we're losing. We don't fully understand what Voyager 1 is measuring because the measurement methodology was designed for a different universe, the universe we thought we lived in. We built instruments to detect what we expected to find. Now that Voyager is finding completely different phenomena, we're having to reinterpret the data retroactively, try to understand readings that were never supposed to show what they're showing. And we're running out of time to ask new questions, to reprogram the spacecraft with new measurement protocols, to gather the data that could actually answer the questions we should have been asking all along. The silence is coming. Not in years, in months really, if you account for the time needed to design, approve, and execute new commands, given the 23-hour communication delay each way. Every message NASA sends to Voyager 1 now is potentially the last meaningful communication with our greatest explorer. Every command has to matter. Every kilowatt hour of power has to be used for something that could potentially change our understanding of cosmic reality. So what happens next? What happens in the months before Voyager 1 goes dark? What new phenomena might it detect? What additional boundaries might exist beyond the ones we've already discovered? What is waiting at the edge of our solar system in the regions we've never been able to observe directly until now? And more importantly, what do these discoveries mean for us? What do they tell us about the environment our planet exists within, about the forces at work around us that we've been completely blind to? These are the questions that should be driving scientific discussion right now. Instead, they're being asked quietly, in small groups, in emails marked confidential, in meetings behind closed doors. The public story remains sanitized, focused on the romantic notion of the spacecraft's journey, rather than the genuinely alarming implications of what it's finding. Voyager 1 has penetrated the boundary of everything we thought we knew about our place in the cosmos, and what it's discovering on the other side is forcing us to completely reimagine cosmic physics, solar system structure, and planetary protection. And we're losing the ability to understand it just as things are becoming most critical. That's not coincidence. That's not just bad timing. That's the reality of deep space exploration. By the time you reach the frontier, your tools are failing, your power is fading, and time is running out. Voyager 1 reached the edge of everything, just as we were finally equipped to ask the right questions. The silence will come soon, and after that silence, we'll be left alone, wondering what our greatest explorer saw in those final moments before the darkness took it. What remains to be discovered beyond this boundary? What additional structures are waiting in the regions Voyager 1 won't live long enough to fully explore? These questions will define the next generation of space exploration, but they will be answered only if we're willing to truly confront what Voyager 1 has already revealed, that our understanding of cosmic reality was fundamentally incomplete, and that the truth about what exists at the edge of our solar system is far stranger and far more consequential than anyone has been willing to publicly acknowledge.